Hello, everyone, and welcome to the remote sensing. Just a second.
Although it's not written in the program, but there is a dinner there. I'm not sure where, probably here in the area. But go by the smell and you will find the dinner. Okay?
Okay, so let's start. So, hi, good evening, everyone. And thank you all for coming for the second session in remote sensing for environmental sustainability and climate change. And we've got several very interesting lectures. We will start with Ariel Meroz, correctly, from the Hebrew University in Jerusalem. Here, sorry.
You need it? Speak like that? You don't speak to the mic, the Zoom one. Okay, thank you very much for coming. My name is Ariel Meroz at the Hebrew University. The lecture is called Evaluating the Impact of Traditional Land Uses along the Ariel Development. The work is being done by myself, Professor Noam Levin of the Hebrew University, and Chi Yin of Kent University. Some background. As we all know, traditional land uses are a big part of the DNAs of the Negev. And not only in the Negev, on the region at all, it means Jordan and Egypt as well, and the West Bank. It's very common to see a shepherd walking around with his herds in all of this region. Many studies have been conducted on the impact, the pros and cons of traditional land uses. And since the satellite imagery era, the remote sensing has itself contributed many researchers to that field. We all know this famous work by Uterman of 1974, evaluating the different impact which the different land evolution caused by different land uses on the border between Itzana and Israel. And ever since that important paper, many other papers have been published on the same short section, fascinating section, and adding much knowledge to that. We have decided to follow the same line of thought, but to extend the research far beyond the Nitzana border, crossing all of the borders all of the borders surrounding the Negev, means Egyptian border, Jordan, and the West Bank, and we added exclosures. Exclosures are the large military bases which are within the Negev, and if we look on this MODIS NDVI imagery, we can see that we can identify the Nitzana border, but if we take a closer look, we can see that the three military bases in the north are bolted noticeable as well, without just by identifying in the eye, a little bit higher NDVI values inside than the surrounding area. In addition, the West Bank has its own marker on the map, and this is an imagery taken. This is the footage taken from the Israeli Air Force industry base while a botanical survey. And I don't need to show you the fence sign. You can see the two differences between the interior side and the exterior side. So our study area is the Negev area and the surrounding and the buffer zone of the surrounding countries. The area crosses the semi-arid, arid, and the hyper-arid zone, and a variety of different soil. In short, the traditional land uses and grazing inside Israel and the surrounding countries. In Israel, what's supposed to occur is spring grazing. Spring grazing, it means that the herds should go from February until May. This is giving the natural vegetation the time to grow, spread the seeds for the coming year. All the grazing, most of the grazing is concentrated in the north of the Negev, where the main Bedouin population sits at, and not south of Mitzpe Ramon. So basically, the central north of the Negev, mostly in the north of the Negev. In our neighboring countries, the grazing occurs all year long without any time limitations, and everywhere in the open land. We added the exclosures and the protected areas. The protected areas are for us the buffer zones near the borders on the Israeli side, and the military bases which are used as exclosures, where we know that one type of land use occurs inside and not outside of it. Or the opposite occurs, or grazing occurs outside and not inside of it. Our methodology that we use, the GIS experimental sampling method, we wanted to observe the borders in a similar geographical way that we could have along curved lines. So we generated dots, evenly spread dots along the border lines. We formed the Voronoi, we used the Voronoi triangular method, and we clipped them according to the distance that we were aiming to. From this, we get a couple sets of polygons, interior side and exterior side, each coupled ones. And they, of course, cross all climate zones and types of soil, and we have that data. So we can always compare the same out of both sides. From that, we got 3 types of polygonal sets. The Israel borders, Egypt, Jordan, and the West Bank. Interior means inside Israel, exterior outside. The military bases, the exclosures inside the military bases is the inside, outside is Israel for this. And the third data set, which you cannot see here, follows the West Bank wall, which is a little bit different from the West Bank 1967 line. And I'll show you the advantage of having 2 border lines a little bit ahead. We added the limitation of using the Ma'arag, special limitation using the Ma'arag 2017 land use and cover map, excluding all data which had agriculture or build-up. We created the data using the Google Earth Engine platform. We used the Landsat and the MODIS. From the MODIS, we used the NDVI product. We used the MODIS albedo maximum and albedo minimum per pixel per each hydrological year. Okay, and the same, similar to that, we use the Landsat max and the Landsat minimum per pixel per each hydrological year. It means from these 4 products, we have a mosaic of imagery which depicts the vegetation cover, whether it's for the perennial vegetation or the annual vegetation, and the continuous vegetation growth based on the MODIS and DVI. We excluded the following data. Wherever the yearly or the multi-yearly standard deviation was lower than 0.01, we weren't sure that we're looking at something that fluctuates for the year. We wanted to have something that has a biological, ecological fluctuation. So we excluded any data that the STD was lower than that. And the results. I'll start now following the Israel borders at the semi-arid region. We have here the 5 parameters, imagery parameters, twice. Once for the interior side, one for the exterior side, one for the interior side. So this is the MODIS and DVI interior, exterior, Landsat max, Landsat min, albedo max, albedo min. And this goes as well for the rest of the climate zones: semi-arid, arid, and the hyper-arid. Again, 5 products twice: interior side, exterior side, darker color interior, lighter color exterior. And beneath here we have the level of significance. And from a very short perspective, while looking on that, we can see that in the semi-arid region, in 5 cases, in 3 out of 5 cases, we can see that the interior side was much more vegetated than the exterior side. The levels of significance here, according to the NDVI, Landsat max, and Landsat min. The arid climate zone, 5 out of 5, the interior side was more vegetated than the exterior side. The arid climate zone covers the Nitzana. And for us, what surprises us that we could identify the same trend going in the hyper-arid climate zone. In 2 out of 5 cases, but the significance was very high, where the interior side was more productive ecologically in the interior side versus the exterior. And I draw this 0.1 line, and this is usually is being used as the presence of vascular vegetation. And all of the results in the hyper-arid for the NDVI, all of the results sits or very close to it or beneath it. So we are not sure that we are observing the vascular vegetation, but we are observing something which fluctuates through the year, which means it's something ecological. This is another way to look at the same results by slicing it according to the borders. And here we count the number of polygons which are significantly higher on one side compared to the other side. This is the interior side, and this is the exterior side, compared by the 5 imagery products that we use for Jordan, Egypt, and the West Bank. And here as well, we can see, for example, in the MODIS and VI, counting more than 80% of the cases, the Israeli side interior side was higher significantly than the exterior side, were about 10 or 15% of the cases. This is now for the West Bank wall results and the bases, or we looked on the Israel borders. West Bank wall sits on the semi-arid region, and in 5 out of 5 cases, in all incidents, it was very clear that the interior side was much more vegetated than the exterior side. I will show you soon how come this huge difference is created over here. Let's move to the arid for the bases, which sits mostly on the arid climate zone. Here as well, 5 out of 5 cases, it was very clear that the interior side is much more vegetated than the exterior side. Moving to the hyper-arid zone, where we didn't think that we will find any significance, any trend, and we find the opposite trend, where the exterior was more vegetated than the interior. I will soon explain our thoughts about that. And again, the same results being sliced a little bit differently. Interior side versus the exterior, West Bank wall. In some cases, 100% of the polygons in the interior side were, according to the MODIS and the VI, Lancet Max and Lancet Min, were more vegetated in the interior side versus the exterior. And this is true for the 4 bases. Nuclear plant is a little bit not as clear, but still tends to the Israeli side, to the interior side, sorry. And there are two of the southern bases act differently, Ramon and Dovda. And I'll elaborate in a second. The West Bank wall. So the West Bank wall, the results were very conclusive. Why the interior side is much more vegetated than the exterior. It sits where the main JNF plantation sits at. So of course, the interior side will be much more vegetated than the exterior side. But the West Bank wall gave us another point of view to observe, which is about here and occurs as well here. If we will look at where the interior side, the green and the red side, the exterior side, before the wall was built, we cannot identify any clear difference between the two sides. Shepherd going around from the West Bank, crossing to the other side basically, and doing grazing on both sides. 2015, very clear to the eye that one side has become much more vegetated than the other, just by putting the wall here, preventing from shepherds to cross this barrier. If we look at that graphically, we can see that the red and the green polygons over here on the y-axis, and the difference between the two on this purple. And in this purple line, and about since 2010, when the wall is built, difference goes up to higher peaks that it has ever been before for the perennial vegetation. And we can see basically that the recovery time for the perennial vegetation occurs here in the semi-arid region, about 2 years after, a year or two, it's already been very significantly in the interior. Higher than the exterior side. Some discussion and conclusion. First of all, I want to elaborate a little bit about the method that we use, the JS sampling method, that enable us to gain a wide overview and gain local insight of what occurs. Measuring systematically all along the borders, comparing types of soil and types of climate zones. I haven't shown you here the results regarding the types of soil because of time, because of the schedule, but we can gain a lot of local insights using this method. Israel borders show significant constant trend favoring the interior side versus the exterior side, crossing all climate zones, and most importantly, being able to identify that occurs as well in the hyper-arid region. It means mostly in the southern part of Egypt and most along the Jordan border between Israel and the West Bank wall. The West Bank wall, of course, gave us the conclusive results, which showed us in one side vegetated, forested, much more vegetation on one side compared to the other side, but it gave us the ability to evaluate the recovery time for the annual and perennial vegetation after grazing has stopped. Military bases have shown a very high consistency between the interior versus the exterior side. And this is to our understanding, is attributed mostly to that the basin sits in the central of the Bedouin population, where very intensive grazing occurs all year long, and not as should be as spring grazing, but actually all year long grazing. Aside from the two southern bases, Ramon and the Ovda. So Ramon and Ovda could be observed. We didn't expect to see any difference between the two sides. If we take a closer look at the Ovda base, we see that a water barrier is built when the base was formed, probably to prevent flash flood coming in from south, and diverting all of the water to the sides of the base, creating a more productive ecologically environment outside the base and not inside the base. Probably if we look at measurements of the Corona of 1968, we wouldn't find these differences. In addition, it sits in a kind of a very distinctive two different geological environments. Thin rocks from the outside and the alluvial fan from inside. So that might as well cause this anomaly that we see. The Ramon base, it's on a plateau. Again, very differently geographically, the interior versus the exterior. So most of the water are being drained outside the base. And if we'll take a look at the Corona of 1968, we'll see that it had a very productive wadi here, which was pretty much disappeared. Only in this short section here, which we know that has been some restorations by the GNF, we actually see that the interior side was higher than the exterior side, more vegetated in the interior versus the exterior. So in the two cases that didn't follow our initial assumption, we could explain, we could find the explanation. Thank you for all the support that I got. Thank you.
Yeah, so I have a couple of questions. First is fairly simple. Which collection of Modus products were you using? Was it 5 or 6? Because there's a big difference between the two.
Okay, Terra or Aqua?
No. Collection in terms of processing.
The collection of the Modis?
Yes.
I
Collection 5 or version 5 versus collection 6 or 6.1 now. Okay, so that's something to look at.
This is
the problem of relying on Google Earth Engine.
Okay.
It's not an archive, it's a data service, and you don't necessarily know what you're using. Okay, so that's one thing. The second thing is, if you use the albedo product, why didn't you use the NBAR product to calculate your vegetation index?
We looked at a few. We were aiming to look at the start. We used the NPV, vegetation cover. 3 products that are coming with the the Modis says as well: the PV, photosynthetic vegetation, bare soil, and NPV.
Yeah, NBAR is the normalized BRDF corrected reflectances. Okay, and what I was expecting you to say is, well, what you used was at a higher spatial resolution. But if you're using the albedo at 500 meter, then why not use the BRDF 500 meter? Okay, so those were. But the real question I have for you is, it doesn't look like you corrected for spatial autocorrelation, and I'm skeptical of a lot of your results as a result of that. Maybe you did correct and you just skipped over it as part of the technical side.
For the
Okay, we can talk later.
Yeah.
The question?
How does spatial autocorrelation apply to static measurements? Answer your response to your
Spatial autocorrelation?
they're static, but
Right. So, I mean, the problem with spatial autocorrelation, if it's positive, which it happens with any patches, you're reducing residual variance, which is going to increase your risk of committing a type 1 error and rejecting the null hypothesis when it is in fact true. This is a constant challenge in doing remote sensing statistical analyses.
Thank you all. So the next, The next lecture is by Professor Arnon Karnieli from Bird Institute, Ben-Gurion University.
Thank you, Karim. Karim said I'm going to talk about mapping wildfire scars, and I would like to compare several vegetation of fire indices, the NDVI, NVR, and the AFRI. And probably all of you know that the wildfires cause a lot of damage and the environmental losses, especially human life, damage to flora, fauna, other consequences. So the main goal of the project is to develop a methodology to detect and map wildfire when the fire is actually active, and also others smoke, and also during the recovery phase. That means the recovery of the fire scars. Obviously, by the literature, the NDVI is the well-known and the index is used a lot for different applications, also for detecting the fire scars. The NDVI is the normalized ratio difference between the reflectance in the near IR and the red. And here in these two images, you see the difference before fire and after fire, and no doubt that the NDVI looks can detect the area that was affected by fire. Now I'm asking, why not NDVI? Looks okay. So there are several reasons. First is that the NDVI is sensitive to dark soil background, and for instance, the fire scars, the wet soils, etc. Here the NDVI versus the soil albedo. When the soil albedo, it's low. Sorry, it's the soil exposed, so there is a difference between the soil albedo. When the LAI is high, see no change in the albedo, in the NDVI. The second reason is that the NDVI is saturated by high value of chlorophyll, biomass, and index. We see this, and we know this exponential shape of the curve. The biomass red, the LAI in blue, and the chlorophyll in green, all of them showing a saturation after LAI value. It's about 2.0. Third is that the NDVI is sensitive for atmospheric influence. In the shorter, relative short wavelengths, there is more scattering. In the relative long wavelength, there is more absorption. So our hypothesis is a use of vegetation indices that uses smear bands, either the 1.6 or 2.1 micrometer instead of the red band, could improve the detection of wildfire under smoke conditions. And there are few physical basis for this hypothesis. The first is that the two smear bands, 1.6 and 2.1, are located in the atmospheric windows, and therefore are less influenced by atmospheric gases like C2, C3, O2, O3, water, and CO2. The second is that the smear bands are rather far from the Earth's peak emission at 10 microns, and thus are not affected by uncertainties in the correction of emitted radiation. The first is the sphere bands are much larger than the size of most of the common types of aerosols, such as smoke or sulfates, but not dust, of course, and consequently penetrate the atmosphere column even if this aerosol exists. And the fourth one, maybe the main important, that the action when of vegetation to stress, when the vegetation is under stress, the reflectance level in both the red and the sphere bands moving in the same direction. That means high, they are higher than the healthy vegetation. Now, we are not the first that thought about this solution. The normalized burn ratio, NBR, is the index that substitute the red band by another sphere bands, either the 1.6 or 2.1. So here we see the difference again of the same burned area. This is the NDVI with the high values on the NDVI after fires in red. And here we see the NBR, which are providing much more details. So no doubt that the NBR is better than the NDVI. Now, we thought about other solutions. We took the NBR, but we divided the 2.1 bands into half. We are taking half of the value and putting this this equation, we call it AFRI, atmospheric free vegetation index, and when the reflectance in the air subtracted by the 0.5 of the reflectance in the 2.1, normalized by the summation of this. Why we are doing it? First of all, because the vegetation cover doesn't influence its independence of the vegetation cover. We see this high correlation between the reflectance in the visible band, this is the red, this is the blue, and the reflectance in the 2.1 micron. The second, while doing this, meaning the NDVI 1.1. This is the NDVI, this is the AFRI 2.1, and we see a very, very high correlation of R equal to 0.98. So let's test this hypothesis or this approach. The first test was an experiment that was conducted by NASA by flying the Everest instrument over a wildfire in Brazil in 1995. Here we see the visible image of this fire. When we are using the sphere band instead of the RGB, the true colors, we see that the atmosphere is penetrated. We don't see anything. In the visible, we don't see anything beneath the smoke. Here, the smoke is clear. We see the ground and we see the active fire. Now, when we are calculating the NDVI, we see the dark area. Here it's in blue, which this is the smoke itself. When we are calculating the AFRI, we see the surface without the smoke and the active fire. This is the second experiment. We use now MODIS with 3 indices. Let's ignore the EVI, but we compare the NDVI with the AFRI before fire. Okay, this is a cross section here. Here is the vegetated area, forest. And here is the forest, and this is the fire. Here is the active fire. Image of MODIS. And again, we getting a very, very high correlation between AFRI and the DVI. What's happened during the fire? During the fire, outside the smoke, this area, in this area, we see again the high correlation. However, when beneath the smoke, the NDVI in red drops to this level, while the AFRI so outside the smoke, we have again very high correlation, and beneath the smoke, these are the points, because the AFRI remains in a high level.
Hello everyone, my name is Christos Theocharidis. I'm a research assistant in Aerospace Center of Excellence and also a PhD candidate at Cyprus University of Technology. Today, my presentation is monitoring forest health through remote sensing time series analysis to assess the effects of extreme drought events in forest seasonality. So, satellite image time series have contributed notably to monitoring forest phenology and forest health. And we can see also how the temperature changes over the time. What we can say about temperature is the dominant controlling abiotic factor that affects plant phenology, where the global climate warming is increasingly disrupting the natural phenological patterns. With the temperature, we have the drought. The frequency is increasing in many regions worldwide as a result of climate change, which has been linked to water scarcity. After that, we have a heat stress and water scarcity, which is expected in the Mediterranean and will increase the frequency of forest mortality events affecting the forest diversity. The main research objective in this presentation is to monitor possible forest seasonal changes due to drought or other extreme events, which we will see later on. The main area of interest or my research is the Paphos forest, which is located in the west part of Cyprus, and concerning specifically the northeast, east, and southeast areas. The materials that I have used are 71 Landsat-8 images and 181 Sentinel-2 images with a time frame of April 2017 to December 2021. For the Landsat 8 satellite images, I had 14 missing values, which I will fill them as we can see here. And for the Sentinel-2, we had 6 missing values. This is an example of NDMI. In order to select the most appropriate method to fill the gaps from 2 imputation methods, I made the Cook distance plots, where here you can see that we have the outliers above the red line. But despite the fact that there are more influential points in the Kalman filter than in the simple moving average, the influence is higher in the simple moving average graphs, and the time series are smoother with the Kalman filter, as we will see later. So for this reason, Kalman filter was selected for the all the time series and vegetation indices and LST. It is noted that for the LST time series, there were no influential points at all. So, a comparison plot between Kalman filter and simply moving average, you can see it is clearly evident that the red lines are with Kalman filter and created much smoother time series rather than the simply moving average. And here is the original LST. When I mean LST, it's land surface temperature. and decompose the time series of LST into trend component, we can see that we have 11 negative trend line slope. A lot of people think that the temperature is rising, but please note that the research is concerning only specific areas. So the monthly, after run the monthly LST red lines assessment, we can see here that January, June, and September have the highest slope percentage, where the most unstable months with the highest standard deviation is June and July. Now, decompose the LST with the BFAST method and the classical decomposition method. One break was detected with the BFAST. It goes on May 2019, which was 30.5 Celsius, which was the second highest May of the time series, where after that June and July were the lowest summer months in the time series, as we can see here in the seasonal plot. The first circle is the LST break, and after that we have a quite significant drop for June and July, which are the lowest summer months in the entire time series. Continuing, these are the original time series for EVI, Hazard Vegetation Index, PCI, Green Chlorophyll Index, and DMI, Normalized Difference Moisture Index, and decompose them into trend component. We can see that they are, according to their trend line slope, they are quite constant. Specific goes not big. I think the time frame of the time series. I will explain it later. Here we can see for every we have 0.5 negative trend line slope, for the GCI 0.2 positive trend line slope, and for the NDMI 0.04 positive trend line slope. So here with the same method, we can see that January, February, and November for every are the highest low percentage, and the most unstable months, the highest standard deviation are January, February, and December. Continuing DCI, March, May, September are the highest slow percentage, and the most unstable months are February, November, and December. And the last NDMI, it's very constant, but as we can tell, January, May, and September have the highest low percentage, and the most unstable months are with the highest deviation are August and December. Now, decomposing the EVI and GCI, no break was detected from BFAST. But with NDMI, we had 3 breaks. The first break was March 2018, which was a dust event in March 2018. Of course, we will see later the first break. The second break was on January 2022. Here we can make the assumption that it was detected because it was the highest NDMI of January's, and we had also at the same time the lowest LST in the time series. And for the third break, I cannot be sure now, so it needs more exploration. Let's focus on the first break, March 2018. On the March 2018, we have a dust event, specifically on 4, 5, and 6 March. But this wasn't only the dust event. We had also a second dust event in the same month. Here you can see from the left side, the left image is a true color. The dust core in the day is in the middle, and at night is the right image. What we can say about dust particles may block the leaf stomata, affecting by interrupting gas exchange process, reducing the photosynthesis, and increasing the absorption of near-infrared or solar spectral irradiance leads to an increase in leaf temperature. This leads to a reduction of the transpiration during the midday and an increase of the water loss at night. And the continuation of exposure to dust will negatively affect forest health, accelerating the forest destruction process. So it is also clear evident the dust event. In the every seasonal plot, we can see with a circle, it's the dust event. Later on, the April and May is constant, and later we have a small drop for June. But for NDMI, after the dust event, we have the lowest April of the time series for NDMI. And for GCI, we have the lowest, after the dust event, we have the lowest value in the entire time series. I think that it tells us that maybe this is the right assumption for the first break that we saw already fast. So after that, we made a comparison. We can see that we can see the LST with EVI, LST GCI, LST and NDMI, and all the indices together. So the highest correlation between LST, EVI, GCI, and NDMI was for NDMI and GCI with 0.85, and with LST and NDMI with minus 0.84. So, and the lowest was GCI, between GCI and EVI with 0.47. And cross correlation with LST and all the indices, vegetation indices, we can see that for the lag 1 and 7 have the highest cross correlation coefficient. For the LST and GCI, lag 1 and lag 2, and for the LST and NDMI, lag 1 and lag 2. Conclusions for this presentation: despite the fact that the NDMI trend line remains constant, showing no significant changes, the maximum value that we had in the entire time series for NDMI was 0.21. I think that it's indicated that we have a high water stress in that area. The highest correlation occurred within LST and NDMI, and as I told before, the time frame of the time series should be extended, of course, in order to see and detect more accurately abnormalities in the trend regarding the heat stress in the area. The bigger the time frame is, the more accurate the data are, in my opinion. And the dust events with the absence of precipitation after these events can affect negatively the forest seasonality, leading them to forest degradation and death eventually. Future work, here you can see the descending as we saw together, but the future work is to extend also the time series, the time frame, and to utilize also Landsat 5, 7, 8, 9, and more Sentinel-2 images, and maybe planet scope imagery should be explored. Assessment and comparison with other vegetation indices will be made, and different elevations in the area, and specifically assessment of areas that only Pinus brutia is growing in that area should be explored, and in order to find also with the elevations possible microclimates in this area. Thank you for your attention.
We have time for several questions. Anyone?
What was the spatial resolution of the Landsat data that you had, the thermal?
30 meters.
30 meters, but Landsat 8 Tiers has a spatial resolution of 100 meters. It's then been downsampled to, or upsampled, depending how you want to talk about it, to 30 meters. And this is part of the challenge of getting products that are already kind of processed out there. So you're already introducing some issues in, uncertainty and spatial autocorrelation into your analyses. So that's something to be aware of. The other thing is that it appears on Landsat 8 has some issues, right? They can't do the split window because of stray light problems. If you can try to correct those, and people argue about how effective that stray light correction is. The tiers 2 data are much better, but that's something to focus on. Use the best sensor data and don't try to push not very good data too far. And the emissivity estimation that you need, to get out good land surface temperature retrievals is much tougher and frequently not talked about. So just some considerations to think about.
Thank you very much. I will ask you later after the presentation. Have fun.
Any other questions?
Thank you very much.
Okay. So the next lecture will be by Gabriel Mulero, detecting weak response to elevated CO2 and drought use in remote sensing analysis.
Good evening, everyone. Once again, my name is Gabriel, PhD student in the Faculty of Agriculture. We're presenting this. Hope we have some insights also at today's discussion. As a background, the current CO2 levels, which is at about 418 ppm, has been projected to rise to about 550 ppm and even more by the end of this century. On one hand, many studies have shown that this increase in CO2 levels should increase yield. And that's because an increase in CO2 should stimulate increase in carbon assimilation. So, on the other hand, if we consider the all wheat growing areas and the 40% dry land areas right now, which has been also estimated to increase to about 60 to 70% by the end of this century, there will be a contrabalance in the yield that has been projected with the increase of CO2, like I just mentioned. So the motivation here is to basically understand how wheat would respond to interactive effect of CO2 and drought basically. But we will be using remote sensing metrics to get input parameters for crop models. So I would just want to introduce to us the RUE Monteith model, which actually predicts gross primary productivity or the crop biomass using as a function of the absorbed photosynthetic radiation and the radiation use efficiency as a factor. So radiation use efficiency is a very important factor here because it helps us, it tells us how the plant exploits radiation for photosynthesis. So we can use, based on many studies, we've seen that we can use PRI to model radiation, to monitor radiation use efficiency. And this is because under light stress, which reduces photosynthesis and also reduces radiation use efficiency, xanthophyll cycle here is affected because the plant tries to escape the damage from excess light. And so the xanthophyll cycle happens. And this xanthophyll cycle affects the absorption, the pigment change affects the absorption at the 531 band. So it makes it easy for us to monitor radiation use efficiency. And that's one. Another model by O'Leary actually predicts wheat yield based on the actual transpiration and transpiration efficiency. And transpiration efficiency here talks about the amount of biomass that can be produced per every unit of water transpired. And so, since thermal images, actually, since I would come back this way, since plants transpire and energy is released, the leaves are cooled. And so we think, based on what we've seen in several studies, that thermal imaging can actually give us a broader view at different scales, plant operative cooling. So we could use this, succeed at this. Another issue with crop models, so now we're talking about the metrics for the parameters, but also in crop models, there is a basic assumption that sunlit areas is actually representative of the whole canopy response. But in reality, there is actually differences in the vertical canopy profile when you talk about the plant biochemical changes, traits, or physiological traits. So for us in this study, we have divided our wheat into different layers: flag leaf, leaf 1, and leaf 2, just based on the nodes. So it has 4 nodes. Here we only consider 3 because the last part dies out early. So we say, since there are variability across the crop vertical canopy profile, we want to see if we can understand what is happening with radiation use efficiency, transpiration, and even our metrics, different canopy layer. So I'll summarize questions as: how does elevated CO2 levels, drought, influence our ability to monitor radiation use efficiency? How does it also influence our ability to monitor evaporative cooling via thermal imaging? And how does this metrics and this important traits for crop models change across the crop canopy? So we set up a controlled experiment. Temperatures were controlled, the relative humidity was also controlled, and in one room, we increased the CO2 levels by 150 ppm, what we estimate for the next mid-century. Then we simulated well water condition and drought, 40%, and also we used Israeli wheat. During the season, we took gas exchange measurements from which we calculated the radiation use efficiency. And then we used spectral imaging using Spectrum IQ, which ranged from 400 to 1000. And we derived our PRI from there. We also did thermal imaging, from which we derived the temperature and the temperature difference of the leaf to the air. So these are some of our results. In the ambient conditions, we see a consistent linear relationship with PRI and radiation use efficiency, although not very significant, not very strong, but significant, and it's consistent with what we see in the literatures. However, under drought, we do not see any linear correlation at all. It's not even significant at all. This is the first time we are seeing this with wheat. We have seen it's been shown in these studies in trees, but we've not seen it in field crops. But we see it here in wheat, and we ask why. So we think that since xanthophyll cycle is what drives PRI sensitivity, if under drought, xanthophyll cycle is actually sometimes minimized by other heat dissipation mechanisms like photorespiration and some other mechanisms. And so once that is downregulated, the sensitivity of PRI is decoupled. So that's what we see here. And so that explains why there's a decoupling under drought. Interestingly, under elevated CO2 conditions, under drought here, we do not see this decoupling. And that makes it very interesting for remote sensing as a remote sensing metrics for the future. But under drought, with more CO2, it means we can actually monitor radiation use efficiency. When we go ahead to check the multi-layers, I'm showing here a table of the p-values of the correlation layers. Under ambient CO2 conditions and elevated CO2 conditions, we see significant correlations. But under elevated CO2 conditions, we do not see, again, under drought, we do not see a relationship, but we see here for elevated CO2 conditions for the flag leaf. We do not see it in the leaf 1 and leaf 2. That might be because xanthophyll actually changes with leaf aging. So we see it here. It means that xanthophyll is still working. For elevated, ambient and under drought, xanthophyll totally out of the way. We're really hopeful, but we need to even dig in more. For the transpiration, so we show here the transpiration and then the temperature difference on the leaf evaporative cooling, which is the temperature difference of the leaf surface and the air. And we see what is the expected from several studies that as the leaf transpires more, there is cooling. And for the ambient and elevated CO2, there was really no difference. But I want you to look at this. For the ambient CO2 conditions, we see, for the elevated CO2 conditions, we see them tilted more to less transpiration and warmer temperatures. And because that is actually what is the expected, more CO2 will drive reduction in the stomata conductance and it might affect the transpiration. So that's what we see here. Every of the scholars are the dates. Now when we go to the multi-layer results, this is also interesting because we've mentioned that the flag leaf does not represent the whole canopy. And we see a change with cooler leaf on the flag leaf and warmer as we go down the canopy. This is interesting in itself. And we see that for a latent heat of, here we represented transpiration as latent heat in its energy term, and I will show you why later. For a latent heat of 350 watts per meter square, we have a range under ambient condition 10 degrees Celsius. But under elevated CO2, first, there's a consistent cooler leaf and flag leaf and goes up that way. But we see a narrower leaf temperature. This has big implications, but I won't talk so much on that because we ask ourselves why. Because we have almost the same range, 350 watts per meter square range of latent heat. Why this temperature difference? We try to think about considering the total energy. If we consider the total energy being a function of the sensible heat flux, the latent heat, and even the metabolic heat flux, which is negligible, we can say that there is the same energy in both rooms since they were controlled. Having this, having this H, I want to explain H again here. For the same latent heat flux, right, for both rooms, 350 watts per meter square, H being the driver of the temperature difference, we can combine the equations and then eliminate the similar terms. And we will see here that what drives the temperature difference between the two rooms, the leaves in the two rooms, is a function of the aerodynamic resistance. Now, the aerodynamic resistance is driven by wind and by the leaf characteristics, which affects its capacity. But in these two rooms, we have the same conditions. Wind could be relatively constant. And so we thought this might be the leaf about the leaf capacity characteristics. So what did we do? We decided, okay, let's check the leaf thickness. Because here we could not destroy the plant because it was a limited sample size. We did leaf thickness of both leaves in both rooms. And we saw that under elevated CO2, we have thicker leaves. And under ambient CO2, I mean, if you compare it to significantly thicker leaves under elevated CO2 conditions, I want us to do something in our head. Multiply for a weak leaf, multiply that, the effect of that on reducing the temperature to about 4 degrees difference, multiply that by the width producing area. That has great implication on the world energy, global energy balance. Just saying from this anyways, we've not tested that. In conclusion, we see that PRI relationship in wheat is preserved under drought due to high CO2s, and leaf temperature is less responsive to evaporative cooling under elevated CO2 conditions. And the PRI, radiation use efficiency, leaf temperature, and the evaporative cooling actually changes linearly across the width vertical leaf profile. Also, we're setting up right now a phase experiment in the field because we've seen what happens under controlled conditions, but we're not sure what will happen in the field under where the conditions are not, there is the wind, there's the temperature that can vary throughout the day or even weeks. And so we hope to get interesting results from this. Special thanks to everyone who contributed in this and to my supervisor, Dr. David Ellman, and thank you for listening.
Thank you. Questions? Anyone? Yes.
Firstly, are there any women in your lab group?
Interesting. Someone just joined.
Yeah, exactly. And secondly, does the added the elevated CO2 scenario, does the added leaf thickness divert from resources from wheat that we eat production?
I'm not sure I totally understand.
The leaves would be thicker in the elevated CO2, right?
Yes.
How would that affect the rest of the wheat plant? Would it divert biomass from, I don't understand, wheat husks or?
So I think I understand it because one of my colleagues, is not here in this picture right now, but he actually did on this same experiment, he did more of crop physiology, and we see that what we expect is that there should be more yield. But the biomass in under elevated CO2 was more, but didn't translate into more yield. If we think about that, we're really curious to see why. Maybe there is translocation of the carbon to somewhere else other than the grains.
You told us to do that mathematics in our head about the area or thickness on temperature, world's temperature. So how would that affect total atmospheric radiation? Would that we're implying?
I'm saying that if we see just from what we have a reduction in the temperatures. So take for instance the ambient CO2 conditions which we have now to be this range of 10 degrees Celsius. What will be the implication with elevated CO2? And we see a reduction. So I'm really curious to see what would be this implication. When we did the what's called energy balance, we see that it's a factor of aerodynamics leaf characteristics, but under a condition that is not controlled, that might be different because there is the wind. So the total calculation right now, I can't give an answer for that, but I just try to do in mathematics to see that if this is consistent under field conditions.
Question? Do you try to look also not just from the goes from the documentation to water use elevated school? Or you didn't look on the water evapotranspiration relationship?
We've not looked at the evapotranspiration relationship yet, but for the transpiration efficiency, because actually water use efficiency using this device is just
The proportion between
GDP and evapotranspiration. So right now we do not have that, but maybe in the field.
Thank you. Okay, and the final talk will be mapping wildfire risk with the orbital imaging spectroscopy, uniform spectral analysis, and an atmospherical correction approach with Dr. Nimrod Carmon from NASA and California Institute for Technology. Welcome and welcome.
Hey, thanks everyone for staying so late. I hope you're still awake. My name is Nimrod. I actually finished my PhD here in Israel in Tel Aviv University. Then I moved to California for a postdoc at JPL, and then they hired me. And here I am now. So this project is about mapping wildfire using imaging spectroscopy, and I want to thank Garrick here for the support of this research through the LC-LUC program. So in Israel, we have kind of severe wildfire that are increasing in frequency. And here we identified 3 regions in Israel that we're going to focus on. And we're going to also focus on the problems with current higher risk products. And the main problem is that these products are low resolution and are given in a smaller time gap before the fire season occurs. So those are 2 main problems that we want to focus on. And the idea is that if we give an estimate of the fire risk enough in advance, it would let people enough time to figure out how to mitigate and rearrange resources and try to reduce this risk. So this is what this figure is about. And so another layer of that would be how to translate in just an empiric map that tells you what the risk is, how to translate that into something useful for the end user. And so there's an aspect of this communication strategy also in this work. But how are we going to estimate the fire risk? And how are we going to create a fire risk map in high resolution? And how are we going to do that enough in advance that is beneficial for the end users? So we're going to combine different observation systems from orbital platforms. But what I'm going to focus on in this talk is sort of new generation retrieval algorithms that can estimate the fire risk on a per pixel basis. So here we have a study site at Mitzpeh Nesuah, and really this slide is just to discuss what is a hyperspectral image. What is the value per pixel that we get from these sensors? And the value is in radiance units. So it's a measure of radiation. But the measurement occurs either airborne or on top of the atmosphere. And you have a lot of scattering and absorption occurring in the path length. And you have BRDF effects on the surface. There's a lot of things that occur that are beside like the point that we care about, which is the surface conditions. So my work at JPL focuses a lot at improving and implementing new physics and algebra into the atmospheric correction routine in order to provide scientists with the best product that they could use to estimate different conditions on the surface. In this case, it's plant traits, but really there's so many other applications, minerals, soils that we heard here, water, and snow and ice, and many, many more. And what I'm going to present here is going to matter for all of the applications, not just the vegetation. So the pipeline that is implemented in most operational products, you always start with the radiance measurement. There is a phase before that deals with radiometric calibration. But let's say we started the radiance. From radiance, we move to reflectance using atmospheric correction. And then we have another step that people that are experts in modeling the reflectance, let's say, of tree canopies using other models. So those are other experts. And the thing is that you need to connect the surface reflectance product with a vegetation trait model. And this is not obvious that the product that we give these scientists is exactly what they need that comes out of their models. And the idea in this work is instead of doing this 3-phase pipeline is to implement a vegetation trait model inside the atmospheric correction routine as an end member for the retrieval. So we're going to use ProSail as an example. ProSail is a model that estimates vegetation traits reflectance, and we're going to implement that inside the atmospheric correction. So it's more stable in retrieving and inverting the plant traits from radiances directly it's also more cost effective in terms of the calculations. So, but still there are other end members in the pixel. So we've discussed today a few times the problem of unmixing. So each pixel gonna usually have a mixture of soil, photosynthetic vegetation, and non-photosynthetic vegetation usually. And you can imagine if you're going to use some plant trait model that knows exactly how to simulate a reflectance of the canopy, that if you have actually in your pixel soil, it's gonna sort of skew the estimate. And yeah, so as Taryn showed us earlier with the scale up from drone to orbital, this is a real problem. So the first question is how to deal with that. And the approach that we came up with is called P-college rings, is a dimension reduction to emphasize the analysis of mixtures. And it's in review right now. And so I show here three spectra. And I think everybody already, if you just close your eyes, imagine how a vegetation spectra looks like, you imagine something like that. So what does that mean? It means that there's too many bands for the same amount of information. I mean, there's spectral autocorrelation. So, and that means that you don't actually need to estimate the reflectance at each band. So in this case, we have 425 bands. You don't actually need to estimate that. You can use a low rank model because all vegetation looks about the same. There's too many bands for not enough data. And that would help you in an inversion strategy if you're using optimization. And the same thing is true for soil and for NPV. Soil more or less look like that. Okay, maybe there's more iron oxide, less iron oxide, maybe there's clays, but the overall reflectance is autocorrelated. And the same with non-photosynthetic vegetation. So the idea is to leverage this fact using PCA models that we're gonna reproject back to reflectance. So we're gonna take large spectral libraries of each of these end members, build a PCA model, and instead of solving the atmospheric correction problem for 425 bands, we're going to solve it for the scores of the PCA models. Once we have that, we can then go back to reflectance quite easily. So in terms of numerical optimization, it makes much more sense to do, much more cost effective, and achieves, as people like to say about PCA, 99% of the variance. So it's a very nice trick to use here. There is another problem in atmospheric correction that people try to avoid because it's a hard problem, and that's topography. So if you look at an example here, we have a pixel in the center of this image, and that pixel has a normal direction to its surface. So that means that the direct solar flux needs now to project on a larger area. But the diffuse solar flux from the sky, that's mostly scattering, stays constant. This variation is extremely important in terms of the illumination radiation onto the pixel. While most of the atmospheric correction products assume a flat surface, actually accounting for this effect is super important for application that requires high fidelity in the spectral signatures such as vegetation traits. So maybe for minerals, it doesn't matter because you're either going to see the coloring feature or not. But for vegetation traits, it's very important to capture. So here we have a study site in Pasadena in the Caltech campus. It's the roof of Beckman Auditorium. It has the same surface on the roof. It's the same material, and it's a symmetric shape. So let's see if I can do, yeah, okay. So A and B panels are the actual radiance measurements from an average next generation. It's a hyperspectral imagery. So if you just look at B, those are each individual pixels plotted here, and the color scale is from a LiDAR instrument that measured this cosine I angle, the angle between the sun and the normal to the surface. So this appears to be just a magnitude shift over the roof. But in fact, if you're gonna remove the mean spectral shape from the roof, you see that the sun facing side, which is from the northeast, is illuminated by the sun, and it's more yellow than the northwest. Northwest. I'm from the side, so it's hard to say. Which is illuminated more by the diffuse illumination, which is more blue as the sky are. And if we look at the spectral variations here, we clearly see the separation. Now imagine that your reflectance changes with this shape, how many errors in your planned trait estimation you're going to get, right? Or how much errors you're going to get from misestimating your error source, for example. So this is a big effect. So the way we manage to account for it is using this PCA trick with the unmixing, because now we have so much fewer free parameters in the model. We can introduce this cosine I angle, this angle between the sun and the normal direction, as a free parameter to the inversion, and we retrieve it directly from the image, from the radiance, without any prior information. So this is the roof of Beckman. The left side is just a LiDAR estimate from a 1 meter LiDAR. And the right side is from radiances. And you can see the agreement between the two estimates. Now, we did the same experiment on a different region in California, next to Santa Clarita. This is a highly rugged terrain area. And maybe I could let you guys think what is from radiance and what is from LiDAR. I'll tell you that these from the SRTM 30 meters. So A is from radiance and B and C are from LiDAR. In the agreement, I didn't put the scatter plot, but it's 0.994 R squared. So what we can say is that we can now retrieve topography from radiance with an equivalent accuracy to LiDAR. And that's, so the reason why it's important is for atmospheric correction, because even if you're going to use the best LiDAR you got, you're going to be a misalignment in the temporal acquisition, spatial resolution, spatial alignment, while from radiance you have absolute agreement between the data sets. And I think that was the last slide. Oh, okay, next step, sorry. So if you remember the mixture model here with the PCA, the plan to retrieve vegetation traits is to replace the PCA model for vegetation with the parametric model of vegetation trait. So I'm going to use ProSail. And ProSail simulates top of canopy reflectance given the different traits of the plant. That way we can derive these vegetation maps directly from radiance using this algorithm. And eventually we're going to combine the estimates of vegetation traits into fire risk and estimate the fire risk on a per pixel basis in very high resolution, and incorporate also historical satellite data. And eventually the objective is to be able to predict fire risk into the future using this historical base. That's all I got, and I'll take questions. Yeah. Questions.
So very interesting presentation. Really like that trick you did there. The question I have with the PCA, were you using the covariance or the correlation matrix?
So it's a covariance-based PCA model. Yeah.
But for a lot of fire risk models, I wasn't quite getting, fine fuel moisture is super critical. And it was not clear to me how you would get fine fuel moisture from this analysis?
Right, so this project just recently begun. First, I'm going to focus on this retrieval of all the vegetation traits I can estimate, and then look at the different indexes and learn. Either use these indexes or learn from historical fire data that we have here in the Israeli forest from the forest. The color is the forest. JNF. And learn a model using some database algorithm. But I'm open to use any other modeling approach that you might propose.
It just might be helpful to look at some of the process-based fire behavior models to kind of see what are the critical things, because to inform the people who fight the fires, I'm thinking about the structure in the United States where we have many, many more forest fires.
Yeah.
They're wanting some kind of standardized parameters, and being able to provide that sort of thing from remote sensing would be extremely valuable.
Right. The idea in this project is to provide an estimate in advance, so communities could kind of rearrange and do mitigation, not necessarily like live fire confrontation. Yeah.
So this is to help inform
And
setting
to
of
give the product
property risk premiums. Right?
for communities at risk.
Any other question? I've got a question.
Yeah.
Did you consider using texture? Was one of the most important.
Right.
Did you consider using additional texture parameters?
Right. So we were thinking about texture because if you look at the difference between the radiance-based estimate and the DSM-based estimates, there is a salt and pepper pattern. And we think that our algorithm actually retrieves topography and texture. So we have to find a way to disentangle this, probably using BRDF models that are going to be implemented. But it is a problem.
This the reflectance, or it is?
So that's the cosine I angle. The angle between is the cosine of the angle between the normal to the surface is this angle, the phi angle.
Okay, but how did you create this product? It comes from
So
airborne imagery, basically.
B and C comes from LiDAR, and A comes from airborne hyperspectrum.
Airborne hyperspectrum.
Yeah.
And you can deduce the
From that. Yes, in an accuracy comparable to LiDAR. That's
Did you measure the
No,
differences? Did you measure the differences between the LiDAR data and between
So that's why we have these B and C plots here, because there's slight differences. We thought that because the radiance measurement observes the surface as is, including the stuff that are on the surface. And if you have in a DEM, which is panel C here, removes all of the surface features. We were trying to figure out what is exactly that we're seeing. It's very close to both, but there's slight variations. So it's an open question. I mean, we do see this again salt and pepper pattern for A that is not all the way explained, but
you have to have מטרות שטח. Do you need to have local measurements?
No. It's a radiative transfer based correction. A little bit similar to ATCO.
Thank you everyone for the great talks, and I think that you've got a bit longer break. So enjoy your break. Thank you for joining us.